Today we will discuss phase equilibrium. So, what is phase rule? Phase rule is an important tool used for the quantitative treatment of systems in equilibrium. According to J. Willard Gibbs, the phase rule states that if the equilibrium in a heterogeneous system is not affected by gravity or by electrical and magnetic forces, the number of degrees of freedom f of the system is related to the number of components C and the number of phases P existing at equilibrium with one another by the equation f is C minus P plus 2. F is the number of degrees of freedom here, and C is the number of components, and P is the number of phases. So, F is the number of degrees of freedom. Now, what is the derivation? So, now we discuss the derivation of the phase rule. So, consider a system of C components. We denote the C components like C1, C2, C3 up to Cc. So, the subscripts 1, 2, 3 etc. denotes component 1, component 2, component 3 and so on, distributed between P number of phases. Okay. So, P is the number of phases here. So, we denote P phases like alpha, beta, gamma, delta and so on as shown in this figure. So, you can see, okay, so for component 1, it can be present in all phases like alpha, beta, gamma, delta and so on. Similarly, for component 2 also, component 2 also is present in alpha phase, beta phase and so on. So, assume that passage of a component from one phase to another does not constitute a chemical reaction. This is very important. So, there is no chemical reaction going on, only the phase transition is taking place. The state of each phase of the system is completely specified by the two variables temperature and pressure, and also by the composition of each phase. In other words, the state of each phase is specified by temperature and pressure as mentioned before, and x1, x2 like this, where xi's are compositions of the components. So, the total number of variables is thus C times P plus 2. So, in equation 2, in this equation, not all the variables are independent and the sum of all must equal unity. So, if we add all the components like so x, x1, x2, x3 in alpha phases must be equals to the x1, x2, x3 in the beta phases and so on, and they are equal to 1. Okay. In other words, sum over I xi p gives 1, where I goes from total number of components 1, 2, 3 etc. So, here as I mentioned, so 1, 2, 3 etc. they represent components. For all the phases, all the P phases separately, there are thus P relations of this type. So, there will be P number of relations of this type. Again, for complete equilibrium to exist between the phases, the chemical potential of each species must be same in each phase, that is mu 1 alpha. So, mu is the chemical potential. We know what is chemical potential. Chemical potential is nothing but free energy change per mole or free energy per mole. Okay. So, mu is the chemical potential here. So, chemical potential of component 1 in alpha phase must be equal to the chemical potential of the component 1 in beta phase and so on. So, chemical potential, as I said, it is defined as free energy per mole, free energy per mole, and mu, we know that mu is an intensive property. It does not depend on mass, like but the free energy depends on mass, but mu is free energy per mole. It does not depend on mass. It's an intensive property. So, anyway, so chemical potential of component 1 in alpha phase is equal to the chemical potential of component 1 beta phase and so on. Similarly, chemical potential of component 2 in alpha phase equals to chemical potential of component 2 in beta phase and so on. So we see that there are p number 1 separate equations for each component. Okay, so for each component like 1, 2, 3, etc., we get p number 1 separate equations. Hence, for C components, the number of such equation is, because we have C number of components, so for each component, we get p minus 1 number of equations. So total number of equations we get for C component is C times p minus 1. Also, the chemical affinity AF, we say, for each reaction at equilibrium must be 0. So if we say the chemical affinity A, if I equals to 0, where I is 1, 2, 3, etc., are up to R prime. This means that there are these many number of equation of this type. Hence, the total number of restricting condition is P plus C times P minus P plus R prime. So the degrees of freedom F that we just defined is given by the difference between the number of variables required to specify the state of the system, that is Cp plus 2, and the number of restrictions imposed by their interdependence, that is in equation 7. Thus, so we can write, so C times P plus 2 minus, these are the restrictions, so we just put it here. So we ended up with this relationship 2 plus C minus R prime minus P. So equation 8, this equation is known as the Gibbs phase rule. If the system is non-reactive, meaning no reaction taking place in it, then the equations of type AF equals to 0 will be absent, that is R prime will be 0. So basically we can omit this R prime because there is no chemical equation is taking place. So the phase rule becomes C minus P plus 2. So this is the general expression we are aware of. So number of degrees of freedom F is number of components times number of phases plus 2. This plus 2 terms comes due to because we considered both pressure and temperature changes. Okay, so it comes from T and P, temperature and pressure, this plus 2 term. Next we discuss phase diagram of one component system. Since the minimum number of phases in any system is 1, it is evident that F is C minus P plus 2. So number of component is one component system, so C is 1, phase is 1 here plus 2, then we get 2. So the one component system is thus bivariant because there are two variables here. Okay, so these are temperature and pressure only. It can be fully defined by two variables, temperature and pressure. If a one component system has two phases in contact with each other, suppose you have liquid water is in contact with water vapor, then component is 1 because you have only water, and there are two phases, liquid phases as well as vapor phase. So C is 1 here, P is 2 here, and this plus 2 term will be there. So we get only one variable, or number of degrees of freedom is 1. So we need only one variable to define the system. Thus, the system is then said to be monovariant. It can be fully defined by one variable, either temperature or pressure. So if we fix temperature, then temperature will, if we fix temperature, pressure will be automatically fixed. Or if we fix the pressure, then temperature will be automatically fixed in order to maintain two phases for one component. Okay, so thus if the temperature is fixed, the pressure of the system is fixed automatically, and vice versa. Thus the system of a liquid in contact with vapor, like water liquid is in equilibrium with water vapor, is monovariant. This is because at each temperature there can be only one and only one vapor pressure. So we discuss now phase diagram of water system, okay, or water only. So water can exist in three forms, that we know, right? So liquid water, solid water, and vapor. Okay, so hence there can be three forms of equilibria. So liquid, when liquid is in equilibrium with vapor, or solid is in equilibrium with vapor, or solid is in equilibrium with liquid. So this is the phase diagram. So we are in the y-axis we are plotting pressure, and x-axis we are changing temperature. So temperature increases in this direction and the pressure increases in this direction. The curve BC. So if we look at the curve BC here, okay, represents the equilibrium between liquid water and the vapor at different temperatures. So here this is vapor and this is liquid, right? So this line, okay, so line BC is the coexistence line of water and vapor. So along any point along this line, you get two phases, okay. Along this line, any point along this line, you get two phases, liquid water as well as vapor, okay, water vapor. But if we just if we consider suppose this point, as I mentioned, if we consider suppose this point here, okay, so along this point, at this point you get both phases, water vapor as well as liquid water. But if you consider this phase here, same point, but if we just increase the pressure, okay, same temperature, but if we increase the pressure here, so we get liquid water. Similarly, if we decrease here, okay, like if we reach this point here, so if we decrease pressure but the temperature if we keep constant, okay, so we get water vapor. Similarly, if we consider if we fixed here, okay, so if we fix the pressure here but temperature if we decrease from this point to this point, so we get liquid water, but this point represents water vapor. Means if we fix the pressure here but if we increase the temperature, so we reached at this point and here only one phase, vapor phase is present. So along line BC we get two phases, but any point above this line or above or below of this line, we get only single phase, either liquid water or water vapor. So the curve BC represents the equilibrium between liquid water and vapor at different temperatures. That's what. So along this line you get two phases. So it's liquid water and vapor both at the phases, and they are in equilibrium with each other. And it is called the vapor pressure curve of water. Okay, so liquid water and vapor both coexist here. So this curve is called vapor pressure curve of water. It can be seen that for any given temperature there exists only one vapor pressure. Similarly, for each vapor pressure only one temperature can be maintained. Okay, as I mentioned here, so for at a particular temperature there exists only one vapor pressure. So this is the vapor pressure along this line. Okay, this is the vapor pressure at this temperature. Okay, this is the pressure. And similarly, for each vapor pressure, suppose you consider any point here, each vapor pressure, there is only one temperature is maintained. So this is the temperature. So that's the degree of freedom F is given by C minus P plus 2. So here number of components is 1, pressure is number of phases is 2, P is 2 here, and this is plus 2. So you get F is 1. The BC curve extends up to the critical temperature of water. So if we extend this curve, we reach at this point. Okay, this is called the critical point, because beyond this temperature liquid water cannot exist. So we don't get any water phase here. If we extend this one beyond this point, we don't get any liquid water here. So this is called the triple point. This is called the critical point. So at the critical point, the temperature is 374 degrees Celsius. And the corresponding pressure is 217.7 atmosphere. The variation of vapor pressure with temperature is quantitatively given by the Clausius-Clapeyron equation. So we know this is the Clausius-Clapeyron equation. It says how pressure and temperature, if we change pressure if we differentiate pressure with respect to temperature, we get this relation. So delta H is the delta H of vaporization, and Vg is the volume of the gas, and Vl is the volume of the liquid. The curve BA, now if we consider the curve BA here, okay, so represents the equilibrium between solid water, or that means ice and water vapor. So here ice and vapor. So again line or the curve AB, any point along this line AB, we get two phases, solid ice and liquid water. Okay, and it is called the vapor pressure curve of ice or the sublimation curve of ice. So this line is called like for BC, we got the vapor pressure curve for liquid water. Here we get the for line AB, for curve AB, it is the vapor pressure curve of ice or the sublimation curve of ice. Again, it can be seen that for each temperature there exists only one pressure. So again, like before, okay, so for each temperature, so if we consider this temperature here, okay, so if we there exists only one pressure. So this is the pressure value corresponding to this temperature. Similarly, for each pressure, so if we fix the pressure here, so in order to maintain this two-phase system, so this will be the corresponding temperature. So again, the number of degrees of freedom is 1. So along this coexistence line, so we discussed so far two coexistence lines, curve BC and AB. So along these lines, okay, we get only we get two phases. Okay, since we are dealing with one component system, so number of degrees of freedom is 1. So you can change either temperature or pressure, not together. Okay. The variation of vapor pressure of ice with temperature is quantitatively again given by Clapeyron equation. This is the same Clapeyron equation. Instead of previously we used delta H vaporization here, and here we are considering delta H sublimation. Okay, so again T is the volume change between the gas phase and the solid phase. Now the curve BD represents the equilibrium between solid ice and liquid water. So if we consider this line BD, okay, again it is the coexistence line of solid ice and liquid water, and again along this line we get two phases. So number of degrees of freedom along this line will be 1. So as can be seen that BD is inclined toward the pressure axis, and the melting point of ice is lowered by the increase of pressure. Okay, so you see it is inclined towards your pressure axis or y axis here, right? So it means that the melting point of ice is lowered by increase of pressure. So if we consider 1 atmospheric pressure here, okay, so 1 atmospheric pressure is somewhere, suppose this is 1 atmospheric pressure here, okay, so this is 1 atmospheric pressure. Now if we increase the pressure here, so this is suppose your 20 atmosphere pressure. So for 1 atmospheric pressure, so this is the melting point, right? This is the melting point, okay, or normal melting point we can say. And for 20 atmospheric pressure here, so pressure we are increasing now, we get another melting point here, we call it MP prime. So we can see that the melting point decreases if we increase the pressure, right? So this is a typical case of for water. For other liquids, usually melting point increases with increasing pressure. So again we use the Clausius-Clapeyron equation. Okay, for ice water, the equation will be dP by dt is delta H fusion by T times change in volume from liquid state to solid state, VL minus Vs. Since the two curves and the line meet at point B, B is called the triple point. So here, so these any two curve we consider as BC or BD. So at this point, all three phases coexist, right? All these 3 points coexist here, because at this point you get vapor, water vapor, liquid water as well as solid ice. So this is called triple point. Okay, so means there are 3 phases at this point. So we have C is 1, P is now 3, and number of degrees of freedom will be F is C minus P plus 2. So 1 minus 3 plus 2 gives you 0. So there is no degree of freedom here. So means the pressure and temperature is fixed, is like at 0.006 atmosphere and 0.01 degree Celsius. We get triple point, means all 3 phases of water will coexist here. Okay, so there is no degree of freedom, so we cannot change pressure or temperature. Still, if we change pressure or temperature, anything like any pressure, either pressure or temperature, then we will not get this triple point. Okay, either we get 1 phase or 2 phase. Okay, so there is no degree of freedom at triple point. So the temperature and pressure B are mentioned in the figure as per the phase rule. So at the triple point, so number of C is number of component, P is number of phases, and plus 2. So we get 1 minus 3 plus 2 gives you 0. So there is no degree of freedom here. So number degrees of freedom is 0 here. The area above the critical point where the distinction between liquid and gas phase disappears, creating a single phase with properties of both liquid and vapor, generates a state of matter as a supercritical fluid. So this is the point. This is the region. It's called supercritical fluid, where you cannot distinguish between liquid and gas phase. Okay, and this is only a single phase here. It has the liquid-like density and solvent properties of a liquid combined with the gas-like viscosity and diffusivity. So here this one, it reaches the supercritical fluid, this region. Okay, so at this region, okay, we get liquid-like density and solvent properties of a liquid combined with the gas-like viscosity and diffusivity. Next, we discuss phase diagram of carbon dioxide. The curve AB. So again, this is the we are plotting pressure versus temperature here. The curve AB. So if we consider the curve AB here, AB is the sublimation curve along which solid carbon dioxide is in equilibrium with the gas. So this is the solid region, this is the liquid region, and this is the gas region. Another striking difference here is between this phase diagram of carbon dioxide and phase diagram of water is, you see this BD line, okay, it is not inclined to the pressure axis, right? It is like it is other way. Okay, if you compare this one, so it was inclined for water towards the pressure axis, but it is away from the pressure axis. Okay, if we see the tilting of BD. So anyway, so we are discussing curve AB. So the curve AB is the sublimation curve along which solid carbon dioxide is in equilibrium with gas. So this is solid carbon dioxide and this is the gas. The curve BC here is the vaporization curve along which liquid carbon dioxide is in equilibrium with gas. So you see this is the carbon dioxide gas and this is liquid. So BC is the vaporization curve along which liquid carbon dioxide is in equilibrium with the gas. The curve BD here, if we consider, BD is the fusion curve along which solid carbon dioxide is in equilibrium with liquid carbon dioxide. Okay. So B is the triple point here. You can see this is the B is the triple point here, where all three phases of carbon dioxide, means liquid carbon dioxide, solid carbon dioxide, and carbon dioxide gas, they coexist, and the corresponding pressure is 5.11 atmosphere for the triple point and minus 56.57 degree Celsius. A slight variation in temperature or pressure at this point may result in the disappearance of one of the two phases. So if we just slightly change the pressure or temperature, we don't get all the three phases. We end up with one or two phases. For example, a slight increase in temperature will result in the disappearance of the solid phase. So if we increase the temperature slightly from here to here, okay, so we ended up with only gas, carbon dioxide gas, okay, keeping the pressure fixed. Similarly, keeping the temperature fixed like along this, so if we increase the pressure here, we get solid carbon dioxide. So we don't get three phases, okay, if we change either temperature or pressure from the triple point. Okay. For example, again, okay, for example, a slight increase in temperature will result in the disappearance of solid phase and the equilibrium will shift along the curve BC. While a slight decrease in temperature will result in the disappearance of the liquid phase and the equilibrium will shift along the curve BA. Okay, so if we change slightly here, we get around this point, okay, so decrease in the temperature. Same for pressure also. A significant feature of the carbon dioxide system is that even at atmospheric pressure, it can directly solidify without the appearance of liquid. Because of this, it is called dry ice. Okay, so 1 atmospheric pressure is somewhere here. So this is suppose your 1 atmospheric pressure here. Okay, this is 1 atmospheric pressure. Okay, so if we now, this is 1 atmospheric pressure here. Okay, so if we change pressure very little bit here, we do not get liquid phase, we get solid phase. Okay. Okay. Similarly, if we lower the pressure here, we get gas phase. We don't get liquid carbon dioxide. Okay, at 1 atmospheric pressure. That's why it is called dry ice. Now another interesting feature here is, okay, so basically we cannot we cannot get liquid carbon dioxide below pressure 5.11 atmosphere. Okay, even if we decrease or if we change the temperature. Okay, so below 5.11 atmospheric pressure, it is not possible to get liquid carbon dioxide even if we change the temperature. Next, we discuss phase diagram of two component system. So for a two component system, the phase rule becomes 4 minus P, because our initial equation was F is C minus P plus 2. So now P is C is 2, right? So this becomes F is 2 minus P plus 2, so gives you 4 minus P. Okay, that's why for a two component system the phase rule is 4 minus P. Since the minimum number of phases in any system is 1, the maximum number of degrees of freedom F is 3. So at least for two component system we get one phase, so maximum number of degrees of freedom of or F is 3 for two component system. Thus 3 variables would be necessary to define a system. So here we need 3 variables, okay, to define a system for one phase with two components. But as 3 is difficult to graph, it is customary to hold one of them constant in the plot of the other two. This reduces the degrees of freedom by 1, and the phase rule equation is now becomes reduced phase rule equation, where F prime is 3 minus P. Okay, so either we fix temperature or we fix pressure. So for a two components solid liquid equilibria, we came across the following cases. First case is the two components are miscible in the liquid state, and the two components are only partially miscible in the liquid state. When we talk about the miscible, means it's completely miscible in all proportions in the liquid state. So we will stick to the former case and under the category discuss. The two components are not miscible in the solid state and form a eutectic mixture. The two components form a stable compound with a congruent melting point, and the two components form a compound with an incongruent melting point. So we first consider simple eutectic system. The points A and B, so this is the temperature and composition plot. So here, as I mentioned, the pressure is constant. So as I mentioned before, so 3 degrees of freedom is difficult to deal with. So either you need to fix temperature or pressure. Here P is fixed. P is fixed here. So at a fixed pressure, we deal with this phase diagram. So here we are plotting temperature versus composition diagram. So the points A and B, here you see point A here and point B here, represent the melting point of components, pure components rather, A and B respectively. Okay, so pure components A and B. So we are varying percentage composition, percentage of B in A. So point here we get 100% A and here we get 100% B. So this point A represents the melting temperature of A and this is melting temperature of B. Okay, and increasing quantities of B are added to A. So here, as I mentioned, so B is increasing. The freezing point of A falls along the curve AC. So if we increase the composition of B along this, so the freezing point of the compound it's decreasing like this AC. Okay, along AC. So solid A is in equilibrium with the liquid component B in A. Okay, so here solid A is in equilibrium with the liquid component B in A. So this is called the freezing point curve of component A. So this is how freezing point changes of A as we increase the concentration of B. This represents like this. Okay, same for the curve BC. For the curve BC here, it is called the freezing point curve of component B. Like for AC, we get the freezing point curve of component A. So BC represents the freezing point curve of component B. So as you can see, since pressure is constant, we can apply the reduced phase rule, and the system is found to be monovalent. So A prime is C minus P plus 1. So is 2 minus 2 plus 1, we get 1. Okay, so along this line, any line, we get 2 phases, and there are 2 components, so only 1 degree of freedom here. The 2 curves interact at point C. So AC and BC, they meet at point C, where both solids are in equilibrium with the liquid phase, that is liquid solution of the 2 components here. The number of phases is 3 here. Okay, you get liquid A, liquid B, as well as the solid solid. Okay, so 3 phases. Okay, that's why the number of degrees of freedom here, F prime, is 0. Thus at C there is no degree of freedom, and it is called invariant. Okay, so you cannot, like a triple point, it is invariant. This means that under a given pressure, the system consisting of 2 solids and their liquid solution can exist only at a definite temperature, and that the composition of the liquid phase is definite. Point C is called eutectic point, or eutectic meaning easy melting. It is the lowest temperature at which the liquid can exist in equilibrium with the solid A and B. So at this point, solid, you have solid A, solid B, as well as the liquid solution consisting of A, component A and component B.